Hi everyone, welcome to Chemistry 12.2. This is the second video for our equilibrium unit. And today we're going to talk about reversible reactions, equilibrium and what we mean by that, and how to describe the position of equilibrium. So if we take a quick look here, this is a lovely clown and he's balancing, and that is a really important concept because equilibrium means something's going to be balanced. If we pop over here, you'll see they may look familiar. These were the requirements or the stipulations needed in order for us to talk about stoichiometry in grade 11. And so we talked about reactions being spontaneous, so we didn't have to wait for them. They were going to occur right away. We wanted them to be fast, right? We didn't want to wait around in the lab waiting for them to be completed, so we wanted quick, fast reactions. We wanted reactions to be quantitative, and this is going to be, and I'm going to use my cursor here. Whoops, not that though. This is going to be what we're talking about here. We're going to see, is this still true? So quantitative means that reactions went to completion, and what we meant by that is all of our reactant would be turned into product. Realizing that one of our reactants would probably run out first, the limiting reagent, and once that occurred, we would have made all the product that was possible. Okay, so this is really the concept that we're going to decide if it's true or if it's a myth. If we had been in school, we would have done a lab to come up with this outcome. And today I'm going to be here to tell you that, guess what? Some reactions are quantitative, but not all reactions are quantitative. Some reactions are reversible reactions, and that's what we're going to talk about today. And stoichiometry, or stoichiometric, so we're using whole numbers for our coefficients. So if you take a look at our next slide, you'll notice that before we can jump right into what's equilibrium or what's meant by a reversible reaction, we need to describe what a closed chemical system is. And a closed chemical system is a system where nothing is entering or leaving. And so often even just putting a cover on top of your beaker turns it from an open system into a closed system. So there may be changes happening within or internally, but there's nothing leaving or coming in from the external environment. That's why with our calorimeters, we had a cover on them. We didn't want any energy leaving, so we wanted to be as close as possible to a closed chemical system. So although there is no net change, there is internal movement, and that is where we're going to see this phenomenon known as dynamic equilibrium. We've talked about it in physics, static equilibrium. We've talked about it in biology, diffusion and equilibrium, the movement between or through the membrane of cells. So now we're going to talk about dynamic equilibrium in chemistry. Okay, so we're going to take a quick look at these chemical systems. When they're at equilibrium, there's constant properties, but it appears that everything might have shut down, but not necessarily. So that's what we're going to take a look at. So just a quick example of open versus close. Here we have a bottle of Coca-Cola. It's got its cap on it. Right, so it's an example of a closed system. As soon as we take that cap off, we know something's going to happen. We're going to see these bubbles. And so we have something leaving from the internal system and leaving outward. So it's gone from a closed system to an open system. And we remove the bottle cap, reducing the pressure, and it alters the equilibrium state so that the CO2 is now allowed to leave the system. Okay. First order of business. What is a reversible reaction? So these are actually the chemicals we would have used in class. We're going to take some calcium chloride. We're going to react it with sodium sulfate. Now that we know a little bit about the collision reaction theory, we know that these molecules are going to be moving and they're going to have proper orientation. And the more successful collisions we can get, the more product we're going to make. And the product here is going to be calcium sulfate and sodium chloride. So this is what we're used to. We've got reactants, we have an arrow, forward reaction, and we are making these products. And up until now, we were happy with that. These guys were colliding and they were making product and everybody was happy. And this would continue on until one of these guys runs out. And then the whole thing shuts down. But I'm here to tell you that there is a new phenomenon happening here. Because if these guys, once they're put into a beaker, are allowed to collide and often have successful collisions, so they're actually having the proper orientation and the proper kinetic energy, they're able to collide and create product. Well, why can't these guys, once we have enough of them, why can't these guys start colliding successfully? Why can't these guys start colliding with proper orientation and significant energy? And why can't they form reactants? The forward reaction is happening, and we've always taken that for granted, but guess what? We have something called a reversible reaction, and a reversible reaction introduces, take that right out, it introduces a new phenomenon for us. So we have these reactants colliding, forming product, but as soon as we get enough product so that we can have successful collisions, there's nothing to stop these guys from colliding and forming reactants. So we start to see a cycle as we travel through, and that's what we mean by reversible reaction. We still kind of read from left to right, so our arrow pointing east is going to be our forward arrow. Our arrow pointing left is going to be our reverse. And so the forward reaction always starts. Okay, that's why I had it covered to begin with. Here we have, right, that's what we're always used to, reactants colliding, forming product. But I'm here to tell you today that sometimes, not always, but sometimes the reactants, once we have enough of them so that we can have successful collisions, those products are going to collide and form the reactant. So at the beginning, we'll only have one direction. Every time a reaction starts, it starts with its forward reaction. And the reverse reaction doesn't happen instantaneously, right? These guys, we have to have enough of them built up, and they have to have successful collisions before they can revert back into reactants. So the reverse reaction comes along later on. And when that reverse reaction comes along, then we tell a different story. So we kind of have this cycle happening. And when this cycle equals each other, for what I mean by that is not amounts, not when the amounts are equal, but when the speed of the forward reaction, so the speed of these guys colliding to make products, is equal to the speed of the products colliding to make reactants, that when that cycle becomes at the same rate, that's when we're going to have equilibrium. That's what's balanced. The rate or the speed of reactants turning into products is equal to the rate or the speed of products turning into reactants. Okay? We might see it written like this. Sometimes it's hard to get both of those arrows, so if you see this on your assignment, that's what it is. It's called equilibrium arrows. These are called equilibrium arrows. And it's just showing you that the forward reaction is happening, but guess what? There's a reverse reaction that might be happening as well. So according to the collision reaction theory, reverse reactions can occur. That is, the products, calcium sulfate and sodium chloride, can react to reform the original reactants. There is a competition between collisions of reactants to form products and collisions of products to form reactants. And when that competition starts happening at the same rate, that's when we have equilibrium. Okay, so there's different types of equilibrium. We have phase equilibrium. And phase equilibrium, you can think about maybe if you've got a pot of soup on the stove, and with your pot of soup, what you'll notice is that soup is essentially made up of water. So when you get it boiling, you'll see that it's boiling, and you'll see there's steam. And what happens is if you take the top of the pot, so if you take your pot cover off and go away several hours, kind of forget that the soup's there, you come back, you got a lot less soup, right? A lot of that water has evaporated, it's left, and it's moved into, we didn't have a closed system, so we couldn't catch it, so it's gone into the surroundings. But if you have your soup and it's boiling, if you put a cover on it, go away for several hours, come back, it looks like nothing's changed. In fact, we have had some change. A lot of that water has evaporated and turned into steam, but the cover caught the steam. The cover's cold, so when the steam hits the cover, whoop, it changes phase again, and it turns back into liquid and drops back into the soup. So it looks like everything has basically stayed like it was in the beginning, but it's actually been quite dynamic. So we've had water molecules turning into gas, and we've had gas molecules turning into water. And when we see that cycle, when that cycle starts to happen at the same rate, we know we have phase equilibrium. Okay, you can have solubility equilibrium. This has to do with if you put a solid into water. It's not a chemical reaction, it's a physical change, right? Dissolving is a physical change. But often if we dump something, let's even, if you're not sure about iodine, we can talk about salt. If you dump salt into a beaker, some of it's going to dissolve into the water, but some of it drops to the bottom. And if you put too much salt in, you kind of have that little hump or a little mound of salt at the bottom. If you go away for 2 days and come back, you've got that same mound of salt at the bottom. So most people are like, okay, well, nothing happened. Well, in fact, that mound has changed over and over and over, because with solubility, there's a limit to how much water can hold salt. So the water molecules are surrounding it, and they're surrounding the chlorine ions and the sodium ions. And so they can only hold so much salt. So if you put too much salt in, the excess drops to the bottom. But it doesn't stay there. There's actually a dynamic equilibrium occurring. And so the water molecules are dropping off old ions of chlorine and picking up new ions of chlorine, or dropping off old ions of sodium and picking up new ions of sodium. So that mound of salt has changed several times, but to the naked eye, it looks like everything stays the same. So the internal system is changing, but the external system is staying consistent. And we have chemical equilibrium, and chemical equilibrium is what we're going to talk about, okay? And we're going to take a look at what is equal. So with equilibrium, something's always equal. And in our case, in chemistry, dynamic equilibrium, it's the rate that's equal, not necessarily the amounts, but how fast these changes are happening. So with chemical reactions, the speed of the forward reaction has to equal the speed of the reverse reaction before we've got equilibrium. Okay, so here you can see you've got some iodine and some hydrogen, and we've got all our reactants here. They're turning into product, HI. So when we start, we have one arrow, right? Our reactants are turning into products. There is 0 products turning into reactants. We don't have that reverse reaction to start. We have to make sure we get enough of this, right? We have to have successful collisions. So if we don't have enough collisions happening, not many of them are successful. But the more and more product we make, the more and more collisions we're going to have, the more and more collisions are going to be successful. So eventually what's going to happen is we have this and I'm just looking for my cursor here, bear with me. Oh, there we go. So we're going to get this reverse reaction kicking in a little later on. And people often say, well, when the amount of this is equal to the amount of that, is that what equilibrium is? And the answer is no. It's not, has nothing really to do with amounts. It's how fast it's happening. So the speed of reactants turning into products, right? That's winning at the beginning, because it's the only reaction that's happening. So the rate is a heck of a lot faster of the reactants turning into products. But as these collisions increase and as they become more successful, right, as soon as those first collisions happen, we've got a reversible reaction there, which I just erased. And I usually have a cursor, and I'm not sure why I don't have a cursor here, guys, but let's see. All right, oops, so that oh gosh, that's bad. That reversible reaction kicks in. We don't have equilibrium yet. The reversible reaction's kicked in, but it's going a lot slower, right? Because there's just not as much of it. So the collisions are happening slower. So it's not until these two reactions are happening at the same speed. That's what dynamic equilibrium is. Okay, so this guy turning into this guy at the beginning, it's really fast. This guy turning into this guy doesn't even exist at the beginning. But once we have successful collisions, we do have some of that product turning into reactant. Until they're happening at the same speed. When they're happening at the same speed, now it looks like to the naked eye nothing's changing, because as soon as you make a reactant, you turn it into product. As soon as you make a product, you turn it into a reactant. So to the naked eye, everything looks like it stays constant, but it's not. We have this continuous change, and that's what dynamic equilibrium is. So I could talk about it for hours, but let's move on. But that's what dynamic equilibrium is. Some people also use an analogy of an escalator, right? So if you're thinking about escalator, and I mean, it's been so long since we've gone out shopping, but let's say we're at a nice big shopping mall and we've got an escalator. And you can think about the people moving up and back or up and down on an escalator. So let's say everybody's on the first floor and nobody's on the second floor. So the first floor being our reactants, the second floor being our products. So a few of our people jump on and they move up to the second floor. We still have lots on the first floor. We have a few on the second floor, and they're shopping around. So we've got a continuous flow of people going from the top first floor to the second floor. But as soon as we get enough people on the second floor, as soon as those collisions start to happen more frequently and more successfully, we're going to start to see some people come down the escalator. Right? So we'll have lots of people going up, a few people going down. But eventually, this system will reach equilibrium. And eventually, we won't have equal amounts on this first floor and the second floor. It's not about amounts. It's about the transfer. So when we have equal people moving up and equal people moving down, so if we have 10 moving up and 10 moving down, now you've reached dynamic equilibrium. You might have 200 up on the second floor and 500 on the bottom floor. But if you have equal amounts transferring between the second floor and the bottom floor, then you're going to have equilibrium, static equilibrium. Okay, so the next thing we want to know about reversible reactions and about equilibrium is how can we put a number on it? How can we numerically give this a description? And what it's called is, can you describe the position of equilibrium? And what that means is, can you tell me, was the equilibrium reached early or was the equilibrium reached late? What we mean by that is, was the reverse reaction able to happen, was the forward reaction able to happen for a long time before the reverse kicked in? Or was the forward reaction only up and running for a short time before the reverse kicked in? So that's how we describe the position of equilibrium. And there's two ways to do it. The first way is with KEQ, or your equilibrium constant. It's going to be a numerical value for you. And the second way is looking at percent yield. You talked about percent yield in grade 11. We're not going to be calculated or anything here, but you need to remember, what does percent yield mean? And percent yield means how much product was created, right? Percent yield, how much product were you able to create? That's where the 99% comes from when we talk about a quantitative reaction, a reaction that is only a forward reaction. There is no reverse one that kicks in. We would assume that it has 99% yield. It's made all the product it could possibly make. None of it was reverted back to reactants. So let's take a quick look at them. So what do we mean by equilibrium position? Indicates whether the reactants or the products are favored in a reversible reaction. So if the products are favored, what do we mean by that, if the products are favored? If the products are favored, what we mean is that that forward reaction was allowed to continue for a very, very long time before we had enough successful collisions with our products so that the reverse reaction could kick in. So that's what we mean by, so therefore we made a lot of products before the reverse reaction kicked in. The opposite is, what if the reactants, and I don't know why that's not blue, because it should be, what if the reactants are favored? And if the reactants are favored, it's the opposite. So if reactants are favored, what we're saying is the forward reaction didn't happen very long at all. It didn't happen, and it didn't get a chance to make much product. And the reverse reaction kicked in, and that product, as soon as we made a little bit of that product, boom, it started reverting back and turning back into reactant. So that's what we mean by products being favored or reactants being favored. When the products are favored, the forward reaction had a long time to occur before the reverse kicked in, and therefore we made a lot of product. Okay? If the reactants are favored, it means we started with a lot of reactant and we didn't get a chance to change much of it into product. So the forward reaction only happened for a short time, and then that product started kicking back and turning back into reactants. I'm just looking at all my typos as I see this. And only a little product is produced. So that's what we're saying with these diagrams here. Okay? So how can we do that using a numerical value, right? So if we want to put numbers onto this, how can we do that? So I don't know why that's not letting me bold that. Guess it did that time. All right. So looking at two different methods of this. The first method is, oh, I forgot to talk about that. Can we kind of sneak back a minute? This is a neat video, a neat slide, so I do want to share with this. We'll get back to percent yield and KEQ. So here's our dynamic equilibrium, a balance between forward and reverse processes. So it's all about the rate. They're moving at the same rate. Even though both reactions continue, the amount of R, so there's your square brackets. I don't know if I mentioned that. Square brackets is a shorthand for concentration. So when you see R with square brackets around it, it means the concentration of reactants and the concentration of products. Okay, so let's see if this picture helps a little bit with this idea of dynamic equilibrium. So if you take a quick look at this, it's from your textbook. This diagram here, the y-axis is concentration. It's always good to know what's on the y and x-axis when you look at a graph. And so the SO2 has a really high concentration to start, and the O2 has a, not as high, but it has a concentration to start. These are your reactants, and that makes sense. We have lots of them to start with, right? Our product, our SO2, is way down here. So our product is actually 0 when we start. And again, that makes sense. So our forward reaction is going to start. And our forward reaction, the SO2, see how it's dropping? And the O2, see how it's dropping? Those guys are colliding with each other. And they're colliding successfully. So the SO2 and the O2 are colliding with each other. So the reactants are dropping in concentration. Why? Because they're making product. And the product's increasing in concentration. Okay? But hopefully you notice here that the SO2, it increases quite drastically, right? We're making a heck of a lot of it, and we're making it fast. But then it plateaus. That's what I mean by this flat section. It plateaus. Okay? All of them plateau. So at some point, this guy stops dropping, and he stays constant. This guy stops dropping, and he stays constant. This guy stops increasing, and he stays constant. There's way more of him than there are of these guys, but they stay constant. This, maybe my circle will work a little better here. This, right? This is when we're in equilibrium, okay? We're in equilibrium here. We have reached it. We have kept this constant, right? They're not changing anymore. And that's because as soon as we take these guys and collide them and make a product, this product collides and makes reactants. So we've got that dynamic equilibrium there. Okay, we've made it. So here you can see that we're starting, when they intercept like that, it means that the reverse reaction has started. It hasn't caught up. It's not going as fast as the forward yet, but when you see those guys intersect, that's when that reverse reaction has started, and then this is where it's caught up, and the reverse and forward reaction are happening at the same rate. I hope that's clear. It's kind of a complicated concept, so I hope you're making out okay with it. So, sorry, back to the two ways that we can come up with, or we can look at trying to describe the position of equilibrium. Let's do this one first. So there's two ways to find the position of equilibrium, or the state of equilibrium. One way is looking at something called an equilibrium constant. The abbreviation is a capital K, a little EQ for equilibrium. So K means for constant. We're going to get a chance to talk about a lot of different Ks. We're going to talk about Ka, Kb, Kw. So this is our first K constant. So it's KEQ. And this is just a generalized equation. A, the lower cases are for your subscript, and the big or capital letters are for your compounds. So we've got, for example, 2 moles of potassium, right? So A would be 2, lowercase a, and capital A would be potassium. So generally, how do you find your KEQ? Well, it's a ratio. We're going to compare a couple things. Essentially, what we're going to do is we're going to compare our products and our reactants, right? And we're going to compare the concentration of them. And so I need a cursor so I can find out where this is. So you can drop down here and you can see, I'm trying to use an eraser here. There we go. We're going to find the KQ and the KQ. That's what we're going to compare, products on the top, reactant on the bottom. Kind of like summation law. Start with your products, finish with your reactants. Okay, and the second way is percent reaction, or I like to call it percent yield. So if you're going to call it percent yield, percent reaction, it means the same thing. How much product were you able to produce? And we use a percentage. So from 1% to 99% is usually the highest we go. So 99% would be creating tons of product, 99% of it. 2% would be creating very little product, only 2%. It also indicates when the reverse reaction kicks in. So if your percent yield is 4%, then it means that you were able to make just a little bit of product, 4% of your max, and then the reverse kicked in and the product started turning into reactant. Okay, so percent yield's pretty straightforward. How is it going to help us to talk about what's favored, the products or the reactants? If you look at percent yield, and I just don't know if it's this slide or the next one. My gosh, how's this turn? Okay. So percent yield, you can bank on this right here. If your percent yield is greater than 50, it means you were able to make lots of product before the reverse reaction kicked in. So when it's greater than 50, we say the products are favored. If it's less than 50, that means that we didn't make enough. We didn't make the threshold. We started making product, but the reverse reaction kicked in and the product started reverting back to reactants. So less than 50%, reactants are favored. So we say it's reached early, right? The reverse reaction kicked in early. So the equilibrium is reached early. Products are favored greater than 50%, reaction is reached late. Okay, I should say equilibrium is reached late. Reactants are favored. And if that reverse reaction doesn't kick in, if it's all forward, we say it's 99%. Okay, these are actually written right on top of the arrows. So I don't know if I have an example, but you can write, nope. For example, well, I won't take the time now, but you could have like, let me do something quick, like oh gosh, let me see if we can do this. So H2 plus N2 yields, and sometimes we draw reverse arrows like that, H2O, NH3, sorry about this, guys, and we need to balance that. I don't know where my cursor is. So we need to, we'll need 3, I'm losing it, 3, and we'll need 2 way over here, right? Sorry about that, but you can see. So the percent yield for this, let's say it's 78. So what we tend to do is we write it, let's say 18, I've already got a 1 there. So it's 18%. We write that percent yield right over the arrows. Now, reactants or products, which ones are favored? It's less than 50%. Reactants are favored. Equilibrium is reached early. Okay, so that's how percent yield works, and it gives us a numerical value. The last thing we want to talk about, I'm going to do it in about 1 minute, is how do we find our KEQ. So a second way of trying to put a number on the position of equilibrium is looking at this general formula, comparing a ratio of products to reactants. So my first product is a C, and the exponent is, or the coefficient is C, so it works as an exponent here. D exponent, A exponent, B exponent. So this is known as the equilibrium expression. If we don't know any of our concentrations, this is as far as we can get. This is our equilibrium expression. Okay, and there are 2 cases when a species is not shown in the equilibrium expression, and that's something to point out. When it's a solid or when it's a liquid or a solvent. So the only compounds that we put into our equilibrium expression are our gases and our aqueous solutions. Solids and liquids, they don't affect the equilibrium constant. It's just the gases and the aqueous solutions. So important to think about that. And if we wanted to actually put some numbers on it, here's an example. So here's an actual equation. N2O4 is being turned into 2NO2. It's reversible. And we're wondering, is the equilibrium reached early or is the equilibrium reached late? We have our expression here. So our product, NO2, the coefficient is 2, so that's an exponent. N2O4, coefficient is 1, that's our exponent. So this is known as the equilibrium expression before you put any numbers in, just showing what your products and reactants are. If you want to go further, see here, they've told me some concentrations. They said at equilibrium, that's the concentrations we want, at equilibrium, 0.0045 moles of N2O4 and 0.030 moles of NO2. Now, earlier they said it was a 1 liter container, so moles per liter is concentration. So this is our concentration. I've just put it in here for N2O4. This is our concentration for NO2. I'm going to square it, and that gives me a numerical value. So, yay, no units, right? This was in moles per liter, this was in moles per liter, they factor out. So KEQ has no units, just a number. And what does that number mean? Well, if you think math, when you have a big number up here and a small number down here, so if you have more product and less reactant, when you take a big number and divide by a smaller number, you always get a number greater than 1. So when your KEQ is greater than 1, we know that the top number was big. We know that the products was big. We know that we had lots of products. So the products are being favored and therefore being reached late. Down here in this case though, we had more reactant than we had product. So we had a smaller number here once we squared it, and we had a larger number here. So we had more reactants than we had products. That gives us a value less than 1. So when the value is less than 1, we know that our reactants are favored. We know that our reactions are, it was reached early, our reactants are favored. So I have that right here. So good to make note of that. Good to know. What does it mean if your percent yield is greater than 50% or less than 50%? What does it mean when your KQ is greater than 1 or less than 1? That's how we can describe the position of equilibrium. Was it reached late? Was it reached early? Were the products favored? Were the reactants favored? That's what we want to talk about when we talk about those things. Okay? And that is it for me. We will pick up and talk a little bit about Le Chatelet's principle in our third video. Thank you. Hope it helped.